All right, folks, I think we should get started. I can see everybody in the session panel. Feel free to ask questions in the chat. I will answer those questions at the end of the presentation. Also, feel free to introduce yourself. Always love meeting people and knowing what kind of work you do and who you work for. So my name is, first of all, can somebody confirm on the chat that they can hear me? All right, thanks, Faraz. Okay, so my name is Emmanuel. I am the CEO and founder of Airtrain AI. And today I want to talk about LLM fine-tuning and why you would want to do it and how the main reason for it being cutting costs. And I'm going to show you how we were able to achieve this with one of our customers. So before we get into those details, I want to go over some basics, like why would you fine-tune and what is fine-tuning in the first place. So at a very basic level, fine-tuning is essentially additional training on top of a base model. So you can use a base model that is either a foundational model that's been produced by any of those model producers out there. You can use another model that's been already fine-tuned to fine-tune it again for something else. But essentially, fine-tuning is applying additional training to a base model. Typically, this additional training uses a different data set than the original one because we want to customize the model to a particular type of data. And so we use a different data set than the original one. If we use the same data set, then obviously this wouldn't have much of an impact on the model. So when you fine-tune a model, you can either fine-tune the entire set of weights that are in the model, but it's been shown that you can also fine-tune a small subset of the weights and get really good results. And that's great news. It means that you can fine-tune models with much fewer sort of resources, compute resources, and much less time, and get really good results out of it. So those techniques are called PEFT, parameter efficient fine-tuning. LoRa is one example of a PEFT technique. Feel free to look this up if you're interested. So the point of fine-tuning model is to customize them to a particular application. So typically it could be making the model speak in a certain tone of voice or look a particular type of output, particular format of output. For example, you could fine-tune a model to understand the input without adding too much prompt around it and having the model return a specific format, for example, JSON or a particular phrase that you're looking for. A label, for example, can be used for labeling, or an XML output or something like that. So here are a few examples of why people use fine-tuning. So the first one is, it's the most common one. When a company produces a base model, typically a base LLM is a completion model. It will take the beginning of a sentence and predict the end of the sentence. So that's useful, but that's not quite what people want when they want to do a question answer. So typically you want an instruct model. You give it an instruction or a question, and the model will return a response. So to change the model from a completion model to an instruct model, you need to fine-tune it on an instruct dataset. So that's one application of fine-tuning. Another one is to convert a completion model, which is the baseline model, into a chat model like ChatGPT, for example, where you can have multi-turn conversations where the user can ask a question, get a response, and then keep interacting with the model within the same session. So that also requires fine-tuning. And that's typically what happens when Mistral produces a model, then within a couple of days, the instruct model and the chat model are also fine-tuned and offered to the community. So another more specific application is to take a baseline chat model, so a model that's already been fine-tuned for chat, and to make it into a domain-specific chat model. So, for example, it could be a healthcare chatbot, it could be a customer support chatbot, a fintech chatbot. That also requires the model to speak in a certain tone of voice. For example, for healthcare, you want the model to sound sort of empathetic and caring, and also not divulge certain information and ask specific questions. You also will need to fine-tune the model for that particular case. And a final example is to turn an uncensored model into a safe model. So an uncensored model will give you response across the entire spectrum, including things that maybe are not safe, whether it's instructions to build things that are not safe or use unsafe words, swear words, or things like that. So you can make a model safe also by fine-tuning it. So these are some of the examples of applications that you could be targeting with fine-tuning. So why you would want to fine-tune an LLM in the first place? Typically, as I mentioned, you want to fine-tune an LLM to customize the model for specific tasks. So, as I said, could be speaking in a certain tone of voice or certain style. It could be understanding your input without a system prompt. So, if you've done a lot of prompt engineering with some of the sort of off-the-shelf models like GPT-4, for example, you need to put a lot of context into your system prompt. You need to explain to the model what is the task at hand, what needs to be done. So, for example, if you have an application that takes in input from a user and you need to return a certain type of output, you typically need to surround the input with your own system prompt. That obviously costs tokens. So these are tokens you need to pay for every time you make a request to the model. And so you can potentially get rid of this system prompt by fine-tuning the model to understand already the task that they have to carry out. So that's another reason why you would want to fine-tune. Maybe you want to generate a specific format for the output. So for example, if you want to have a model that generates a very fixed schema, JSON schema, for example, with specific fields, then you would want to fine-tune a model for this purpose. So you would build a training data set of the inputs and the exact payload in the output, and then you would train the model to always extract the same sort of schema of payload for the output. That's also something you can do with fine-tuning. Typically, fine-tuning is not a good sort of tool for knowledge augmentation. So if you want to teach new information to your model, this is not the best way to go. You can teach new information as you're fine-tuning the model. The model will learn some new information, but the safest way to teach new information to a model is actually not to teach it, but to provide this information as part of the context window, which is RAG, Retrieval Augmented Generation. I'm sure you've heard a lot about RAG. This is the go-to technique to make the model aware of data that the model hasn't seen during training. So fine-tuning is not really appropriate for this use case. It doesn't really prevent you from things like hallucinations or things like that are much better taken care of by RAG. So if you're trying to teach new information to your model, maybe fine-tuning is not exactly what you want to do here. One other reason why you may want to fine-tune a model is to reduce costs. As I'm going to show in the next few slides, you can get really good model quality, model performance from small model, cheap models, if you fine-tune them on high-quality data sets. So you can use potentially a smaller model to replace your big model. Let's say you're using GPT-4 in your application. It costs you a lot of money. You are potentially able to replace this model with a much smaller model, for example, a Llama 3, a Mistral 7B, one of those models, even a Phi 2, potentially an even smaller model. By fine-tuning it to a very high-quality data set, the model will perform equally as the big one on the specific task. So that could be a great way to reduce your cost. Remove those large system prompts, as I explained. You may not need this prompt anymore if you fine-tune the model, so you have fewer tokens, you're paying for fewer tokens in your inputs, and also performance improvements. So you can have faster inference if you have a smaller model, and you can require less hardware. So for example, if you want to deploy a model on device, for example, on a phone, to have extremely low latency and throughput and high throughput for like real-time application on the phone, you are going to need to have a small model. Obviously, those large models out there cannot fit on phones, and so you can have similar performance by fine-tuning a small model, and it will fit on the small device. So these are reasons why you may want to fine-tune an LLM. So if this was not enough to convince you, let me show you those plots here. So those plots come from the website called artificialanalysis.ai. They gather a lot of data from different sources to rank models on different dimensions. On the very left plot here, you see a comparison of quality. This is an aggregate score across benchmarks using a number of different benchmarks like Humanival, MMLU, HealthSwag, and all those kind of industry benchmarks. And they aggregate those into a quality index. So higher is better. So the models that are on the left in this plot are the higher quality model. You can see here GPT-4 Turbo, Claude 3 Opus, and so on. These are the best models on the market. In the middle, you see a measurement of the model performance in terms of actual speed. So throughput, how many tokens per second those models can process. Obviously, this depends on the hardware that you're using. So this is an aggregation of the performance that they were able to measure across a number of different hardware profiles. But this is a ranking of how those models perform. And on the very far side, very right side here, you can see a measurement of price for these various models. And obviously, also this depends on what providers you use. So this website uses some aggregate as well. So what you can see is that the very best models, so if you look at here, GPT-4 Turbo and Claude 3 Opus, are also the slowest models and are also the most expensive models. So that's a trade-off that you have to think of when you're trying to select a model for your application. Of course, it's the easiest way is to start with those very large models that are available through APIs. You only pay for what you use. Very easy, very comfortable, and very developer friendly. However, they will add a lot of latency and low throughput into your application, and they will cost you a lot of money. So this is why you may want to fine-tune models so that you can have low cost and high performance, but for a high quality as well. So to further this argument, I'm going to show you this academic research. This is a paper that was released, I think, in April last year, so just about a year ago, from Microsoft Research. This was the Phi-1 model. So Phi-1 was the first in the family of the Phi models. Phi-2 has been released since then, and recently also Phi-3. And what they were able to prove in this paper is that if you take a fairly small model, so here 1.3 billion parameters, so it is fairly small, and you fine-tune it on a high-quality data set. So here they mention a selection of textbook quality data from the web, and they add on to that some synthetic data. So they mention here a synthetically generated textbooks and exercises with GPT 3.5. So they prompted GPT 3.5 to generate this synthetic data. So they took a small model, trained it on a very high quality data set, something that they curated very deeply by themselves. And the result is that it beats all bigger models except a couple. So in this list on the right, at the very bottom, you can see Phi-1, and it scores 50.6% on the human eval benchmark. And the only two models that beat Phi-1 are GPT-4 with 67%. We don't exactly know how big is GPT-4, but it's probably on the order of 1.5 trillion parameters. So as you can see, like 1,000 times more than Phi-1. And Wizard Coder, a 16 billion parameter model, also beats Phi-1. So this is the kind of the proof that if you take a small number of parameters and use a very high quality data set, you can get performance that is on par with the large state-of-the-art models out there. So I hope this was, I was able to convince you that fine-tuning models can be a worthy exercise for you if you are struggling with cost or quality or performance in your application. So next, I'm going to discuss when it makes sense for you to think about fine-tuning. And then after that, we'll see how you can optimize that to get the best out of it. So getting a good and useful fine-tuned model is actually not trivial. Running the fine-tuning jobs are fairly straightforward. There's a number of tools out there to do this. So running the jobs themselves is not the most challenging. However, your output model will not necessarily be of high quality if you don't have high quality data. So it's kind of an involving process that you don't do out of the box when you're just starting a project. So when should you think about doing it? So first, I would advise that if you're just starting to develop an application, you should probably use the best-in-class models that are served through APIs, like the GPT models, the Claude models. It's the easiest way to get started and prototyping your application. And it doesn't require a lengthy evaluation process to figure out what model to fine-tune and how to fine-tune it and so on. So this is probably the best way to go, is to use one of those off-the-shelf model to build your prototype. And if it doesn't work with GPT-4, this is a saying that's pretty common in the industry. If it doesn't work with GPT-4, just forget about it. If you cannot make your application work through prompt engineering of those very good models, it means your application probably will not work with a fine-tuned model. So I would advise that you use those models first to prove that your application can work in the first place. Then if it does work, before you even start fine-tuning, I would argue that you just ship your application to production and start getting users, because it's not necessarily worthwhile, spending the time to run a fine-tuning experiment if you don't have users yet, or if your application has been launched in production. Once you've launched your application in prod and you're starting to see growth, the users are coming to your application, but your application is too slow or is too unreliable because the OpenAI APIs go down sometimes for a few hours at a time, or your application costs you too much money in tokens, that's when you can start thinking about fine-tuning. So that's probably a good time to consider fine-tuning a smaller model to replace your existing model. So I would encourage you to do those things first before you think about fine-tuning. So what do you need to have in order to have a successful fine-tune? So here's a bit of a checklist. The first thing you need to think about is a very specific, well-defined task. As I mentioned before, fine-tuned models are better as good as larger models, but only on a specific task. As soon as you fine-tune your model, it will get better at the task, but it will lose the generability of your model, if you will. So it will not get better on other tasks. So it will still be bad at those other tasks. So your task cannot be too broad. So if you're just trying to build a generic chatbot, for example, that can understand almost any type of conversation, then fine-tuning would probably not be useful for you here, because the model will become overfit in one direction and will not be able to cover those other applications. So if you, for example, have built an agent or like a RAG pipeline that makes multiple calls to an LLMs for different tasks, so maybe a call for summarization, a call to format an output into another output format, or another call to do data extraction. These are different tasks that you can fine-tune for, but you will likely not be able to fine-tune a model to cover all those tasks. You can try maybe a couple of different tasks, but typically you will have better results if you choose one particular application. So if your product has multiple subsequent LLM calls, I would encourage you to find the one that is the most problematic in terms of cost and performance, and maybe target this particular application first to replace it with a fine-tuned model, and then move on from that. The next thing you need is a very high quality data set. The same as in other ML and data science situations, the quality of your data set is crucial. So you can try to build up this training data set from your prototype. So if you have a prototype in production that uses GPT-4 or any of those big models, you can use this traffic to generate your training data sets. Be careful here in the terms and services of OpenAI. You are not supposed to use their data to train a model. So be careful there. Maybe you can use this data to inspire you and to try to extract some of those logs of your application to build a training data set, but be careful what you do here. Make sure you read the OpenAI terms of services before. But you could be using another big open source model, for example. That's totally fine, like a big Llama 3, for example, to generate traffic and use that as a training data set. So once you have this kind of data set to get started, I would encourage you to look at the data set manually, browse through the rows, try to understand what's in this data set, maybe do some manual labeling, some curation, remove some examples, some rows, and so on. This is quite important. You can also generate synthetic data sets, so you can prompt other models, so better models, to generate a data set. Obviously, that will cost you money, but it's a great way to generate a fairly diverse and high quality data set. Typically, synthetic data is of higher purity and higher quality than whatever you can get from other sources. So this is another thing you need, is a high quality data set. And finally, the third thing that you need for a successful fine-tune is an evaluation harness. That means you need to be able to measure if your fine-tuned model, the final sort of product of your fine-tuning, is of high quality. So you need to have metrics to quantify model quality. So you need to be able to run those metrics on the fine-tuned model. So you need probably to have a test data set, maybe a holdout from your training data set, like maybe 10%. And you need to have metrics to quantify how good the model gets. And maybe you want to compare with ground truth. So if you have a good reference of what is a good answer for a particular prompt, you can have metrics that compare the generations of your fine-tuned model with your ground truth. And so once you have that, you can have a measurement of how good your model is. Without this evaluation harness, you basically are flying blind. You don't know if your model will be good enough to replace your existing model. And so fine-tuning is kind of a useless exercise. So even before starting fine-tuning, I would encourage you to think about your data sets and how you're going to evaluate. So first, even evaluate your existing model. If you're using one of the GPT models, evaluate that to have a baseline to know what you're up against. Okay, so the next thing you need to do once you have this data set and an evaluation harness is to select a fine-tuning mode. There are two modes of fine-tuning. The first one is fairly straightforward. It's called instruct mode. So I talked at the beginning of this presentation about this instruct fine-tuning. It's basically converting a completion model into a question response model. And so in this case, the training data is fairly straightforward. You have two fields: the input, which will be the query that will be sent to the model, and the output, which is the expected response from the model. Here's an example. Let's say you want to fine-tune a model to extract topics from maybe news article. And here's an example piece of data. Here we have an article from the Apple announcement from yesterday about the iPad Pro. And the output in terms of topics would be, hardware, Apple, iPad, for example. This could be one of the rows in your data set, an input that you will give to the model and an output that will generate, that will be what you expect the model to generate. Very straightforward. This is the instruct mode. This is appropriate if you are trying to fine-tune an LLM for a query response type of thing. So for example, sending a large article to an LLM and extracting some highlights that are formatted in the JSON payload, or extracting topics, or extracting sentiment, or things like that. Instruct mode is ideal here. One input, one output, fairly straightforward. The other fine-tuning mode is the chat mode. In this case, you're fine-tuning for a multi-turn conversation where the user will ask a question, the model will return an answer, and the user will continue the conversation, and so on. There could be an arbitrary number of turns in this conversation. In this case, the training data is more of a chat transcript. So it could be a transcript from any of the ChatGPT conversations or anything like that. But in this case, you also need to think about the appropriate chat template for the base model. Each base model has an associated chat template that converts an arbitrary list of interactions, like the one you see here on the right, and converts it to a format that the model can expect as a chat transcript inside the prompt. So many models share very similar chat templates. So usually, it's very straightforward to figure out. But every base model will require you to comply with that particular chat template. So this chat mode this fine-tuning mode is a little bit more complex. Also, evaluation here is a little bit more complicated. But this is another way to fine-tune a model. This is more appropriate, obviously, for chatbot situations. Okay, so now that you have those two modes and you've chosen one, the next thing you need to do is to prepare your data. This is probably the most important thing you need to do. So even before the Gen AI space erupted a year ago in the old school, if you will, ML space, the traditional ML space and data science space, data is always the most important part of any project. So you should spend more time looking at your data than tuning the parameters of your training job, hyperparameter tuning or things like that. Those optimizations are only worthwhile once you have a high quality data set. So I would encourage you to spend most of your time creating your training data set, looking through your training data, understanding your training data. Models are just a representation of your training data. So if you have a bad training data set, you will have a bad model. Even if you optimize the hell out of your model, have the best hyperparameters, if your training data is of low quality, you will get a bad model. How are all those model providers out there providing high quality models, like the Mistral models, OpenAI models, and so on? They have high quality data sets. That's their secret, if you will. So this is where you should be spending the most time, is to look at your data, understand your data, and become one with your data. You need to exactly understand what are the quirks in your data, what are the outliers, the gaps, and so on. So you need to remove and fix low quality data. So typically, if you're scraping data from the internet, so maybe you want to create a data set of Wikipedia articles or maybe Reddit posts or something like that, when you're scraping, you will invariably also collect garbage data, things like HTML tags, JavaScript, all those things that are present on the web, but that are not the actual content that you're trying to train on. So I would encourage you to look through your data set, find those rows in your data set where you have this kind of garbage data, remove it, clean it, lint it, and do all this manually, because you can definitely use tools to inspect, but at the end of the day, you really need to become one with your data. Find all the duplicate rows. If you have rows that are duplicated multiple times, even if it's not exactly the same row, if you have 100 times 100 variation of the same input data, your model will tend to overfit to that particular piece of data, and you will see this in production after you deployed your model. So it's important to find those duplicate rows and remove them. You can use embeddings to do this. Rows that are similar, rows that are the same, obviously will have the same embeddings, but rows that are similar will have a very close embedding. So you can use a vector database to try to do some clustering and try to find rows that are very close to each other, and that maybe you need to remove some of them to keep a smaller sample of those. Same thing with outliers. If your data is mostly concentrated in one particular topic, and maybe you want to fine-tune the model for a medical application, so you have a huge corpus of medical data, and maybe there's like 3 or 4% of your data talks about something entirely different because the way you collected your data, maybe there was some noise and so on. I would encourage you to try to hunt and find those outliers and remove them from your data set. You can also use embeddings to do this. You can find clusters of embeddings in your data set and try to find a few rows that are not part of any clusters, that are just way out there. And then you can remove them from your data set, and it will lead to a much higher quality model. Same thing with your system prompts. So if you are building a training data set using some chat transcripts, for example, from your current production application, and you have some system prompts in there, if the system prompts ends up in your training data set, then it will be replicated dozens, if not hundreds of times across your data set. And it means that your model will overfit to that. So we saw this with one of our customers. Their training data set had a few different system prompts, and we trained on that, and then we deployed the model to production. It worked well, but as soon as they wanted to change the system prompts to different formats, like tune it a little bit, the model became confused. And so in order to fix this, we had to, in the training data, generate variations of the system prompt. So you can use GPT to do that. You can ask GPT to generate variation of a system prompt, and you can make sure that your data set has variations of that prompt so that there's no overfitting to a particular system prompt. So otherwise, you get you need to retrain your model every time you make changes to your prompt, which is not very practical. And then finally, you need to identify underrepresented data. So if you're trying to cover a number of different topics, for example, in your application, and one of those topics is very underrepresented. So for example, if you're doing a medical chatbot specifically for, maybe back pains, and your training data covers a number of back pains, but another one like a sciatica, for example, is not being talked about at all, then your model will basically be blind to this subset of data. So you need to identify gaps in your distributions and maybe generate synthetic data to fill in those gaps so that your data set is representative of what will happen in production. This is actually the most important thing. Your training data should really reflect the actual data that it will see in production. So both in terms of tone, but also content and so on. So I would encourage to do this to your data sets to get better results. So now I want to talk about a case study that we did with one of our customers. And in this case, it was a healthcare chatbot. So it was a chatbot that takes a patient's sort of intake and try to route them, prepare notes for a physician to see them eventually. And so they had built a prototype using GPT 3.5, and that worked well, but there were two problems. One, it was very expensive. GPT 3.5 is still quite expensive at large scale. And also because it's healthcare, privacy was very important. So this customer needed to have a model that was on-premise. It was not okay to send data out to the OpenAI API. So the first thing we did is to establish this evaluation harness. You see 4 plots here. These are metrics that are relevant to this application. I'm not going to go into details to explain what those metrics are, but they were relevant to the chatbot, history completeness, formatting, relevance, and so on. Then we scored the output generated by GPT 3.5 on a scale of 1 to 5. That's Likert scale. So 1 is low quality, 5 is high quality. And you can see all those plots here range from 1 to 5. And so you can see in blue the existing baseline, which is GPT 3.5. In red is the untuned Mistral 7B model, and in green is the fine-tuned version of this Mistral 7B model. And maybe we can focus on the second plot here, the proper formatting. As you can see, the untuned model is pretty weak. It peaks around scores of 1 and 2, so low quality on this particular metric, while the baseline is much higher quality, an average of 4.8, almost 100% at the score of 5. So obviously, there's a big difference here between GPT 3.5 and Mistral 7B. And what's interesting is that after we did this fine-tune on their data set, we were able to get the fine-tuned model to perform exactly as well as GPT 3.5. As you can tell, you cannot see here the blue and the green point because the green point is on top of the blue point, essentially the same score, very high quality, whereas before the untuned model was pretty low. You can see similar effects on the other plots to a lesser extent, but this one is very representative. And so you can see in the bottom right the actual metrics results. So the 4 rows in this table corresponds to the 4 plots that you can see here at the top. And so on the right side, you can see the baseline, the scores for the baseline model. On the left side, you can see how low the scores were for the untuned model. And in the middle, you can see how close the fine-tuned model is to the baseline. So this is to prove to you that what the Phi 1 paper sort of claimed a year ago, we were actually able to reproduce it. With a high-quality data set, we were able to get a small model to perform just as well as a large model on a specific task. Now, let me move on to another case study. So this is the e-commerce unicorn that we mentioned in the title of this talk. So this company are ingesting a lot of product description coming from external merchants to sell on their website. And they noticed that if those product descriptions are well characterized, meaning that they have the appropriate Google product category, then they get better search results and better conversions. So they built a prototype that uses GPT 3.5 to infer from a product description the correct Google product category. So this was all well and good, but at the scale at which this company is operating, using GPT 3.5 was just out of the question, way too expensive. And they also want to have the privacy to have a model on premise. So we also fine-tuned a small model for them. You can see in the chart on the right side here, the results we got. So with the untuned model, the category accuracy, so how many times the model got the correct category for this product, was fairly low, 47%, so less than half the time. And then we tried to do it manually by labeling it manually, and a human was not able to get better than 76%. But the fine-tuned model was able to get 94% accuracy to find the correct product category. This is pretty impressive to go from less than half to almost in a 95% accuracy for this task. So another case in which a small model was able to perform very well. Now, the reason why this company wanted to fine-tune a model was cost. So let me run with you through a cost analysis of why it's so much cheaper to use a fine-tuned model. So let's take as example an application that processes every month 100 million input tokens and produces 100 million output tokens. It could be any application, could be the application that we just discussed. This is the traffic that they get every month. Now, let's say they want to use GPT-4 for this application. So the pricing for GPT-4 is $30 per million input token, and $60 per million output token. So if you do the math, that results in about $9,000 per month in inference cost sent to GPT-4. Pretty expensive. Now, if we take an out-of-the-box small model like Mistral 7B, it's typically about 20 cents per million token input and output. This is kind of an average across the different providers out there. So a baseline untuned Mistral 7B would cost you about $40 per month for this traffic. Very cheap, right? But obviously, this is not a tuned model, so the performance, the quality of the output would be way too low for it to be usable in production. Now, if you fine-tune your Mistral model, typically the inference costs are higher. It's about $1.5 per million input and output tokens. So in this case, it would cost you about $300 per month. So that's already much, much cheaper. Now, if you increase your volume, if you go beyond 100 million, this will obviously increase. So maybe you can think about hosting the model yourself in your infrastructure. In that case, you will not pay per inference, per token. You will just pay per GPU hours. And here's an example of an L4 GPU on GCP. So L4 GPUs can host a Mistral 7B model easily, and it costs about $515 per month to have an L4 GPU deployed, 24 hours a day on GCP. And so, as you can see, if you end up deciding to do this, going from your $9,000 a month inference cost using GPT-4 to hosting your own fine-tuned model for about $500 per month, you have 94% cost reduction. That is a dramatic reduction. You can also use a hosted model, and pay you $300 a month. That's also good. That's also a great reduction. But for identical quality, the same performance of the actual quality of the model, this much higher throughput, so much faster model, more reliable because the model is lighter and hosted in your infrastructure, is not relying on the OpenAI API. It is safer because your data does not leave your VPC, excuse me. And so this is overall a great win. Obviously, there's operational differences. When you use OpenAI, you only have to send a query to the API and get a response. That's fairly easy. If you want to deploy a model yourself, you need to have some understanding of how to deploy a model in your infrastructure and so on. But you can still serve your model from any of the existing providers and still get those great gains. So I hope I was able to convince you that fine-tuning a model can be worthwhile to reduce your cost if you have a high volume in your AI application. So this is essentially what we're trying to do at Airtrain. Just a couple slides to tell you what we do. So we're a team of veteran engineers. We worked at all those companies in the past, and we built AI infrastructure for cruise before. So to train the models that go on the self-driving cars, the cruise cars, we built the infrastructure that supports those training jobs. And so now we are sort of repurposing this type of technology for the LLM space. Our goal is to power this continuous AI data lifecycle. So when you fine-tune a model, if you get good results, that's great, but typically that's not the end of the story. You probably need to monitor the quality of your model in production and then to retrain it every few months, maybe with new data, fresh data, and so on. So this is essentially a cycle. This was always the case with ML. You always need to collect data, try to identify how your model performs, how it fails, to try to correct those issues in your training data set and retrain your model, reevaluate, and redeploy it. So this is the kind of data lifecycle that we're trying to enable with Airtrain. And so we have a no-code platform to help you do this, where you can basically fine-tune your models, evaluate the models, then serve them. And also we have a playground that you can use to compare models. It's one of the most comprehensive playgrounds out there. You can get started for free for about and you can get $10 free credits for this playground, where you can query up to 24 models in parallel to compare quality, cost, and so on. So this is us in a nutshell. Feel free to come talk to us. You can find us at airtrain.ai. You can join us on Slack if you want to discuss your use case and how we can help you. So just to remind you, we do evaluation on your own data set, no-code fine-tuning, and inference as well. So that's it from me. Happy to answer any questions you may have now. So I see messages from Kenneth. So pointing to some data sets. That's very good. Using inspirations from data set out there to start your journey into creating your own data sets. And for sure, fine-tuning and serving fine-tuned models, there's a lot of open source product out there, like, for example, Lorax from Pretty Base, to serve it by yourself. That's something you can do definitely by yourself. Obviously, it will require a bit of skills to deploy those things in a Kubernetes or a VM inside your cloud provider, but it is definitely doable. Here's a question from Chance. Does it make sense to fine-tune an open source model to reduce its inference cost, say limiting the output token counts, for example? Yeah, so that's a good question. As I mentioned in this slide here, the untuned model is fairly cheap already. So you could, if you fine-tune a model typically on platforms out there like Airtrain or other similar platforms, the fine-tune model will cost more to serve. Why? Not necessarily because the actual hardware costs more for a fine-tune model. It's the same architecture, but because the company the service that provides the model that's tuned the model for you obviously needs to make money, but also has to have the infrastructure to serve your model scalably. So one reason you would want still to fine-tune those models is indeed to reduce the token count, to remove potentially your system prompts from the input, and to make sure that your output is exactly what you need and not more. So you can still get some gains through that. In case 2, the manual accuracy was worse than the fine-tuned model. Okay, so let me go back to this case study. So here we don't have the actual accuracy for the baseline. So I'm not sure. Manual accuracy was worse than the fine-tuned model. How was the accuracy computed? Oh yeah, okay. So essentially, this Google product category taxonomy, I don't know if you're familiar with it. It's hundreds of thousands of different product types. It can be like, shoes, sandals, or like home decor, cushions, or things like that. So it's a multi-level, it's like a tree, it's a multi-level taxonomy. And so we targeted here a depth of 3. So we wanted to have a product category that was a depth of 3. And so we measured accuracy by how many segments or how many of those sort of taxonomy segments the model was able to accurately predict. So this is how we measured it. Another question, how would you advise on choosing open source LLM to fine-tune specific data sets? Yeah, so that's a good question. So I would encourage you, depending on the complexity of your task, obviously, I would encourage you to try to start with the smallest possible models. So, the Mistral 7Bs, the Llama 2 and 3, the small models, even potentially Phi 2, Phi 3 if you can, because the smaller model will mean the cheaper inference. Obviously, you need to go through an evaluation process. So you need to have metrics to evaluate how your model performs on those things. The way that we do it at Airtrain, when we need to fine-tune a model, to select a base model to fine-tune, is we use the playground that I mentioned here. We have this playground where we can query multiple models at once. So first, we say that this playground is like a vibe check. It's not like a statistically significant measurement of which model is best, but it gives you an intuition as to which one is best. So we're going to put together a number of models in the same size class. So for example, comparing Mistral 7B, Llama 2 7B, Llama 3 8B, a number of models in the same size class, and then we start prompting the model manually. So copy pasting maybe some data from your training data sets and seeing out of the box without any tuning which one performs best for your use case. Once you have that, either that's good enough for you and you want to go ahead and start fine tuning, or you want to do a more systematic evaluation. And for this, you can also use Airtrain. We have a batch evaluation tool where you upload an entire data set, configure a set of models that you want to compare, and set some evaluation metrics, and we will run this evaluation job for you and show you the results, the distributions for the results at the end. One other factor that I would encourage you to consider when choosing a base model is the existing tooling around it. So why? So usually we choose Mistral 7B. It's usually the one we select. Why? Not only because it is the most sort of versatile, it's the best at many different tasks, so it can be fine-tuned in different directions, but also because the tooling out there, all the tooling is already adapted to the Mistral architecture. So, the fine-tuning frameworks, the serving frameworks already know how to deal with those models. Same thing with Llama 2. It's a very well-known architecture, which means that all the fine-tuning tooling, all the inference tooling will know how to deal with those things. For example, the VLLM inference server, you can easily serve any flavor of Llama 2, Llama 3, Mistral 7B. So I would encourage you to focus on those kind of popular models. If you want to fine tune a more sort of maybe underground, not very popular model, obscure model, then you can definitely do that, but the tooling may not be available for it. So you may struggle a little more. It may be more obscure and less well documented. So that's another thing to consider when selecting a base model. I think we have maybe 1 minute left. So happy to answer any questions. In any case, thank you everybody for joining, and feel free to check us out at Airtrain AI and find us on Slack as well. All right, I think we're done. So thank you very much and goodbye.